Guys, we are looking at section 5.2. This is on page 130 in your student journal. First of all, what does it mean to have simplest form of a radical? Well, we can have no radicands have perfect nth powers as factors other than 1. All right, so if we're thinking of like doing the square root of 27, the factors of 27 would be 9 and 3. Well, 9 is a perfect square root, so I cannot leave it like this and consider it simplified. I would just have to think of this as 9 times 3 and then 3 radical 3. Now I have it simplified because the factors of 3 are 3 and 1, and neither one of those are going to be perfect square roots. It also says no radicands can contain fractions, so I'm not allowed to leave something. If I have the square root of 1/2, I'm not allowed to leave it that way because I'm not allowed to have a fraction under the radical. And we'll talk about how we can rationalize this. I can actually split it apart. I can think of it as square root of 1 is 1 over radical 2, and then I just multiply the numerator and denominator by radical 2, and I get radical 2 over radical 4, which is just 2. And now I do not have a fraction under the radical. No radicals appear in the denominator of a fraction. So back to this problem, I can't leave it like this. I'm not allowed to have a radical in the denominator. This does not have a radical in the denominator. For a conjugate, all we do, this is when we have a binomial. We have two terms. We change the middle sign. So that would be like this. If I have, say, 2 over 1 plus radical 3. Well, I'm not allowed to leave it this way. And the reason why is because it's very difficult to estimate this answer. Radical 3 is about 1.7, but even so, I would have to do 2 divided by 2.7, and that's pretty difficult to estimate. But if I multiply by the conjugate, this is a binomial, I just change the middle sign. If I multiply by that in the denominator, I also must in the numerator. So I would get 2 minus 2 radical 3 all over 1 times 1 is 1. Outers are negative radical 3. Inners are positive radical 3. Last times the last is minus 3. So those outers and inners canceled out because I had a negative radical 3 and a positive radical 3. That was just 0. So now my answer becomes 2 minus 2 radical 3 all over negative 2. And I can split this apart because I have a single term in the denominator. So 2 divided by negative 2 is negative 1. Negative 2 radical 3 divided by negative 2 is plus radical 3. So this beginning value is equivalent to this. And this is a lot easier to estimate now. Radical 3 is 1.7 minus 1 is 0.7. So the whole reason for this multiplying by the conjugate of the denominator was so that estimating would be easier. I mean, now we have calculators, so it's not as big of a deal, but being able to estimate is helpful. So that's why we do that. Like radicals, these are radicals with the same index and the same radicand. So what we're talking about here would be if I have the fifth root of 7, and let's say I have the 5 times the fifth root of 7. Well, these would have the same index. The index is the 5, and the radicand is 7. So because these are like radicals, I would now be able to add them. What would I get if I added them? 6 fifth root of 7 would be what I get if I add them. See, here's the thing. I must have like radicals in order to add or subtract. It doesn't matter, though, if I'm multiplying and dividing. I can multiply and divide no matter what types of radicals I have. Like radical 2 times radical 3 is radical 6. They're not like radicals, but I can still multiply them. Here are some properties. This one should make sense to you. If we have like bases, the rule is we add the exponents. So we're going to be looking at more difficult problems, like 5 to the 1/2 times 5 to the 3/2. The bases are alike, so the base stays the same, and we add the exponents. What do you think the mistake is people make with that? They multiply the bases. So they say this is like 25 squared. No, The base stays the same, we add the exponents. For whatever reason, when we have variables for bases, people don't make that mistake. They know this is x to the 6th. But then when we write it as 5 squared times 5 cubed, they want to put 25. I'm sorry, this would be to the 5th. When they have 5 squared times 5 cubed, then they want to multiply these. But no, see, this is x times x times x times x times x. So that means we have x to the 5th. And here we have 5 to the 5th. The base stays the same, add the exponents. What about if we have a power to a power? Well, that means we have to multiply those exponents and then keep going. This one is a nice rule. This is saying that when I'm multiplying, I really don't have to multiply those together first. I can just do 16 to the 1/2 times 9 to the 1/2. Why is that better than doing 16 times 9 and then to the 1/2? Why is it easier, Karen?
Because you know those are both perfect squares, and if you multiply them together, they might not be a perfect square.
Well, they still will be a perfect square,
Oh.
but it's something else that happens. What happens 16 times 9 is what?
It's a larger number.
Exactly. It's a larger number, and it's going to be more difficult to work with. So why not just do the square root of 16 is 4, square root of 9 is 3. And so what is 16 times 9 then? Look at our answer. What must 16 times 9 be? 144. So this is 144 to the 1/2, which is 12, but it's easier to break it apart like that. All right, 36 to the negative 1/2, we've talked about how if we have a negative exponent, it's going to come to the denominator and become a positive exponent. If we have anything raised to the 0 power, that's 1. When we are dividing, the base stays the same. We subtract the exponents. Here's the mistake people make. They want to cancel out those 4s. No, the base stays the same. We subtract the exponents. So see that? They subtracted those, they got 2, and the answer ends up being 16. What if we have a power of a quotient? Well, we can just separate that. We can do the cube root of 27 over the cube root of 64. And that's easier than trying to think of what's the cube root of 27/64. Okay? So those are all the properties. You can look back as needed. So this is when we're talking about rational exponents. Rational means fractional. So when we have these fraction exponents. The same rules hold true when we have radicals, but just kind of reviewing if we have radicals. It's the same thing. If I instead of multiplying these first, I can separate them. So if I have the cube root of 4 times the cube root of 2, if I could do that, I would. But I can also just say, well, the root's the same, so multiply the numbers, then take the cube root. In this case, it's better to divide this first. They're both 4th roots, so I divide them, and I get 81, and the 4th root of 81 we should know is 3. All right, I want you guys to come down here, and I want you to try these 5 problems now on your own. Okay, what questions do you have over the first 4? I thought number 4 was pretty difficult. So on this one, guys, I said the cube root of 27 is 3, squared is 9. And at first you think, well, there's nothing I can do with these. However, 9 can be written as 3 squared so that we can have like bases. And then when our bases are alike, we add the exponents. So that's 2 1/3. See, whenever we can get like bases, we should. This is considered more simplified than that. Now, if I were writing it in radical form, I'm not. I'm supposed to write it in rational exponent form. But I could have written this in radical form as 9 cube root 3 over 16. Do you see why? We have the number 9. This is 3 to the 1/3, so that means the cube root of 3. And then we have over 16. So this is equivalent to that. So if I'd asked you radical form, you would have done that. All right, let's come down here now. Perimeter. Anyone think they know the perimeter? Karen?
40x to the 1/4.
Does anyone agree with him? Yes? No? He's right, isn't he? Because to find the perimeter, we would add all of these together. So we have 10, 20, 30, 40 of them, and this is not going to change when we're adding. We keep that base the same, and we keep the exponent the same as well. What about for the area? Well, for the area, we're going to have to do base times height. That's one way we could do this. Or we could think of it as 10x to the 1/4 squared. We could do it that way. What's this going to be, you guys? Somebody new? Carter, did you get it?
It's kind of like a guess. 100x
To the what?
not 160.
Okay, so when our bases are alike and we're multiplying, we add the exponents. So what would 1/4 plus 1/4 be? A half, right? So you would get this. Okay. Now the other way I said you could have done it is you can think, since it's a square, you can do your side and you can square it, right? That's another way you can find the area of a square. So we could think of it as 10 squared is 100. And then when I have a base and I have a power to a power, I multiply. See how if I multiply, I'd get 2/4, which is 1/2. So either way, you'll get that answer. Any questions on those 5? All right, let's come over here now. We're going to do some more examples together. So now we're looking at when they're in radical form. Sometimes a problem is easier to do in rational exponent form, and other times it's easier in radical form. Now, one thing I want to point out is being quick with these. Like when you're taking the ACTs and things like that, you have to do 60 questions in 60 minutes. There's no time to waste at all. Even, on other things, like when we're taking a test in here, sometimes people wish they had extra time, right? Well, we got to get you so that you're faster. Here's one way that you can be faster with this kind of problem. It's very tempting to think, okay, I have like roots, so I'm going to do the 6th root of whatever I get when I multiply those two together. Not as fast. Instead of getting larger, we would like to get smaller. So I'm actually going to write 25 as 5 times 5. Do you know what 625 is? Multiplied together, factors? What is it again?
Is it 25 times 25?
It is. It's 25 times 25. So now look at this. We really have a 5 times 5 here and a 5 times 5 here. So if I have the 6th root and I have the 6th root of 5 to the 6th, what's it going to be? Just 5. Okay? That is much quicker than getting out your calculator and trying to do that even. I only want you to use your calculator if it's absolutely necessary. Same thing here. It's tempting to rationalize the denominator by multiplying by radical 7 on top and bottom. Not a good idea. just go ahead and divide. Watch how I'm going to divide these. 34 divided by 7 is 4. Okay? With how many left over? Nope, more. What's 4 times 7? 28. So I have 34 minus 28. So how many are left over? 6. How many times does 7 go into 63? 9 times. So after I divide these, I get 49. And what is the square root of 49? 7. Okay? On this, I could multiply these together, but it's not a good idea. Keep them factored. So I'm going to think of this as the cube root of 25. What are the factors of 25? 5 and 5. What are the factors of 10? 5 and 2. And then on the bottom, I have the cube root of 2. Okay, well, what is the cube root of 5 times 5 times 5? 5. So now I'm going to have 5, and then I just have the cube root of 2 over the cube root of 2. Well, what's going to happen with that? They cancel out, and so our answer is just 5. Okay? All right. We don't really have time to do this one. We're going to do this one, though. This I'm going to split apart. Cube root of 5 over the cube root of 9. Is 9 a perfect cube root? But what is a perfect cube root? 27, right? This is 3 times 3. So I need another 3. So I'm going to multiply. If I do it on the denominator, that multiplication, I must do the same in the numerator. So now what do we have in the top? Cube root of 15. And what are we going to have on the bottom?
3.
Just 3. That's it. Let's go to number 12. What do we do to simplify something like this? Multiply by the, what's it called? Conjugate, yes. So I'm going to have to do 1 minus radical 6 in both the numerator and denominator. So when I multiply these, I just get radical 2. Multiply these, I get radical 12. Multiply these, we get 1. These, we get negative radical 6. These, I get positive radical 6. So that's just going to be 0. And then on the last one, radical 6 times radical 6. What's radical 6 times radical 6? Just 6. All right, so radical 12, though, there's a perfect square root under there as a factor. What is it? 4. So I'm now going to have in the numerator radical 2 minus, if that's 4 times 3, what's it going to be? 2 radical 3. And then it's all over negative 5. And that's okay. I can leave it like that. Or I can think I'm going to divide this, and I can think of it as negative radical 2 over 5 plus 2 radical 3 over 5. Those of you who do the big ideas online, it will be interesting to see which way they want it written, because never quite sure on that. They may have you leave it like this, or they may have you split it apart. All right. All we're going to do down here are 13 and 14. 13, we're adding. We must make sure that we have the same index and the same radicand. And we do, so we can combine them. What do we get? 38 cube root 5. Very easy. On this one, we look. Well, our index is 4th root on both of them, but this radicand is 1250 and this one's 32. We need to have like radicands. I prefer to change this from rational exponent form into radical form. I think it's easier to do the problem in radical form. So now I have to think, can these be simplified? Because I'm trying to get like radicands so that I can go ahead and subtract. What is 1250 divisible by? Easy number. What's the easiest number it can be divided by? 2. So I'm going to think of it as 2 times 12 divided by 2 is 6. 50 divided by 2 is 25. That's what that one is. Let's divide this one by 2. 2 times 16. It's usually small numbers you want to divide by. Is there a fourth root of 625? 5. Something you need to know. Fourth root of 625 is 5. So I take that 5 out and I multiply it by what's already out there. So 5 times 2 is now 10, fourth root of 2. Over here, what's the fourth root of 16? 2, and I multiply it by the 5 that's already there. So that's going to be 10, fourth root of 2. So what's the answer going to be to this one? 0. Okay? And we're saving these last two for tomorrow, a little more complicated. Okay, so that's it for today.